In this video, we'll talk about the issue of repeated roots for solving second-order linear constant coefficient homogeneous equations. So if we have an equation like this one here, y double prime minus 2y prime plus y equals 0, we want to approach this using our normal method for constant coefficient equations and see what we get. Well, for this equation, we have a characteristic equation, which is r squared minus 2r plus 1 equals 0. And this factors as r minus 1 quantity squared. I only get one value here. I get it twice, it's the same factor squared, so this is like this r minus 1 times r minus 1. I would get for my general solution something like a c1 e to the t plus a c2 e to the t. Because I'm seeing e to the t here twice, I've got two factors of r minus 1 in this polynomial. But there's a problem here. This is the same thing as just c1 plus c2 times e to the t, so it's really only one function. And if you work out the Wronskian or any sort of calculation of these being linearly independent functions, these are not. They're the same function. That y1 times y2 prime minus y1 prime times y2 is going to evaluate to 0, so these aren't linearly independent, so I can't actually use it to get every initial condition. So this one solution I get, this e to the t, is not enough. I need to find some way to get some other solution to this problem. As of now, this is a problem that looks normal. It looks like everything else we've been doing before, but I only got one solution from my method. I need to find another one. And the technique we're going to use here is the idea of reduction of order. This is sort of the standard way of getting to a second solution for these kinds of problems. It also works more generally. The idea is the following. So we know that c times e to the t is a solution for any c. Because c is a constant, that's just how this problem works. Now, if I want to solve for the other solution, I'm going to try plugging in y as some unknown function v of t times e to the t to hunt for the solution. We're going to plug this in the differential equation and try to get to an equation that v of t will satisfy. You could set this up in whichever way you wanted to, but the fact that we have this e of t in here that is a solution should hopefully make it so the equation for v is simpler than the one we had for y. And it turns out in this case that is true. It does make the equation simpler, and it'll let us find the second solution. Let's see how it works out for this particular example. Here's the same equation we had before. So we know that e to the t is one solution. So now we're going to plug in y2, this is going to be our second solution, as v of t times e to the t into that equation. Let's start by taking derivatives. So y2 prime is the product rule. And we do the same thing to get the second derivative. It's going to be a v double prime times e to the t plus a v prime times e to the t. Plus, now from the second term, a v prime e to the t plus a v of t times e to the t, or v double prime of t e to the t plus 2 v prime of t e to the t plus 1 vt e to the t. Now we plug all that in. So we get that our original equation equals y double prime minus 2y prime and then plus y. Now let's regroup these terms based on what derivative v they have attached to them. So if we do that, I'm going to get v double prime of t times e to the t, there's only one term with that in it, plus a v prime of t times what? I will see a 2 e to the t from this term. I will see a minus 2 from this term, and that's it. And for v of t, I will see an e to the t from the first term, minus 2 from the second term, and plus 1 from the third term. And if you notice, this and this all goes to 0. Which means I'm left with just v double prime of t times e to the t equaling 0 because I want to solve the original equation equaling 0. Since e to the t is never 0, this leads me to the equation v double prime of t equals 0. It's still a second order equation, but it's a lot simpler than the one before. I know how to solve this one. This is the direct integration problem. This means my solution v of t is just AT plus B for any constants A and B. Those are my constants of integration from this problem. What that then gives me is that my solution y2 is going to be AT plus B times e to the t. We're eventually headed towards linear combinations, so I know that b to the t already works, so I can ignore that part. The important new step in this process is my second solution is this t times e to the t. So that gives me the second solution that I need to try to actually solve these problems. This becomes a second solution that is going to be independent from the first one and will allow me to use linear combinations to meet different initial conditions for this problem. The point being here, to summarize, with a double root up top, we can get one solution just by using our normal method, and the other one ends up being t times that solution. That's how the idea of reduction of order applies to this particular problem in order to find a second independent solution to these problems, and then we can use linear combinations to satisfy all initial conditions, and wrap up this discussion of how to solve all different kinds of these constant coefficient second order linear homogeneous equations.